This is Chapter 11, Basic AC Quantities. Section 1 is Background Information. The difference between DC and AC. DC stands for direct current, and it is unidirectional, and it usually has a constant magnitude. And so by this we mean that the electrons are flowing in the same direction through the circuit. That's what we mean by unidirectional. And they usually have a constant magnitude like 1 amp. That doesn't always have to be constant though. The voltage value could change, and the current is proportional to the voltage, or the resistance value could change, and so if the resistance goes up, the current could go down. So the magnitude is usually constant, but doesn't have to be. The important thing is that the flow of electrons through the circuit is unidirectional, always in the same direction. Alternating current, on the other hand, alternates directions. It is bidirectional, and it continually changes magnitude. It's very rarely ever constant, and it periodically changes in polarity, which again is just another way of saying that it's bidirectional. So sometimes the electrons are flowing in one direction through the circuit, and sometimes they're flowing the opposite direction through the circuit. And they'll flow in both directions. And so that's the difference between DC and AC. And so if we look at these two graphs, in the DC circuit we've seen the schematic symbol for a DC source. The electrons always flow in this counterclockwise direction through this circuit because of the way the source was connected. The electrons always leave the negative, and they'll always return to the positive. And so the current will be a relatively constant value as long as the voltage is constant and the resistance is constant. And so this graph represents that. As time goes on, the voltage value in this DC circuit is presumably always 10 volts, and the electrons are always flowing in the same direction through the circuit. Now in an AC circuit, first notice the schematic symbol for an AC source is a circle with a sine wave in it. And so in an AC source, the electrons start off at rest, and that's what we see in this graph. There's no current flow to begin with. And the voltage gradually increases up to 14.14 volts. As that voltage gradually increases, the current will also gradually increase as well. And so as the voltage is increasing, the current is also going to be increasing with it, and the voltage will, in this example, eventually rise to a value of 14.14 volts. Then the voltage starts to reduce in value, and as the voltage reduces in value, so does the current, and eventually the voltage reduces all the way back down to 0 volts, at which point there's no current flowing in the circuit. And then the voltage switches polarities, and so the negative terminal of the source is no longer negative, it changes to positive, and the positive changes to negative. And now the electrons flow in the opposite direction. So the voltage begins to increase with this reverse polarity, and as it does, the current also increases, but this time in the opposite direction. And so the current now is flowing the other way through the circuit. And after the voltage reaches its maximum value, the voltage will again start to decrease, or I should say increase, because here it's negative, increasing back towards 0. And again at 0 volts, the current in the circuit will be 0. And this pattern repeats indefinitely as long as the source is connected to the circuit. We will continue to see these sine wave patterns of voltage and current in the circuit. So AC is used for power transmission. AC current can be stepped up or stepped down using a transformer, and we'll talk about transformers in a lot more detail in a later chapter. And so this compares the characteristics of AC and DC. Current in one direction only. That's true for DC, but that's false for AC. AC, the current flows in two different directions, sometimes in one direction and then sometimes in the other. The current periodically alternates in direction, 1/2 the time in each direction, so that's true for AC but false for DC. The voltage can be stepped up or stepped down by transformer action. That's true for AC only. Transformers will not work in a DC circuit, and again we'll explore why that is in a later chapter. It is an efficient means to transport power over long distances. That's true for AC but not DC. This goes back to transformers again. When we step the voltage up, the power transmission is more efficient, and since DC circuits cannot be used with transformers, that will not be true for DC, only for AC. And AC is useful for all purposes, whereas DC is not necessarily, for example, power transmission. But AC is very versatile because we will see later in analog circuits that AC can be rectified into a DC current. And so AC is very useful because we can use AC to transmit power over a distance and then rectify that into a DC current at the point of use. And so your computer, for example, you plug that into the wall outlet, which is AC, but that is rectified into DC, and your computer actually operates on a DC current. Most of your electronics are this way, though not all, but most will be. This is a good time to review rotation and measure of angles. Imagine a vector that starts off on the positive x-axis. We'll call that 0 degrees. And if that vector were to rotate a quarter of a revolution, we'll call that 90 degrees. If it were to rotate half of a revolution, that'll be 180. 3/4 of a revolution is 270 degrees, and a full revolution all the way around the circle is 360 degrees. And so these angle measures correspond to the positive x, the positive y, the negative x, and the negative y axes of the coordinate plane. So any angle in between 0 degrees and 90 degrees will be in the first quadrant. Any angle between 90 and 180 is in the second. Between 180 and 270 is in the third. And between 270 and 360 is in the fourth quadrant. And again, an angle like 90 degrees is not in the first or the second quadrant. It's directly on the positive y-axis. And that's true for 180 as well in the negative x-axis, 0 in the positive x, and 270 in the negative y. This is section 2, generating an AC voltage. So if 10 to the 8th flux lines, which is 1 Weber, if 10 to the 8th flux lines were cut in 1 second by a single conductor, that conductor would generate 1 volt across it. 1 volt would be induced across from one end to the other of that conductor. And so if you imagine a conductor that was bent into a coil and was rotating in a magnetic field, the maximum number of flux lines are cut when the motion of the conductor is perpendicular to the flux lines. So when that coil is rotating in a magnetic field, sometimes those conductors are rotating perpendicularly to the flux lines, and sometimes they're rotating and they're parallel to those flux lines. When they're parallel to the flux lines, none of the flux lines are actually being cut by the conductor, and so therefore there will be 0 volts induced across that conductor if the conductor is moving parallel to the flux lines. And so this is what we mean by that. Imagine a permanent magnet here where this is a north pole, this is a south pole, and so the flux lines are directed from left to right. And we have a single conductor bent into a coil, and this coil is rotating within this magnetic field. And so this is going to be an example of a DC generator. A DC generator uses a commutator. And so this part of the conductor is connected to this lighter red colored part of the commutator, and this bottom part of the conductor is connected to this purplish color of the commutator. And the two parts of the commutator do not touch one another. They are insulated from one another, and current cannot flow there. But the commutator does rotate with the conductor, and as the commutator is rotating, these brushes are riding on the commutator. And so as this rotates, sometimes this part of this brush is in contact with the red part of the commutator, and as this rotates, sometimes this brush is in contact with the purple part of the commutator. But each brush is always in contact with one part or the other, and they're never both in contact with the same part of the commutator at the same time. And so imagine that this conductor is rotating with its commutator and brushes. When this part of the conductor connected to the red part of the commutator is moving from left to right through this flux field, none of the flux lines are being cut, and so the induced voltage will be 0 volts. But as we continue to rotate clockwise, this part of the conductor will be moving down through the flux lines, and when it moves down, that is perpendicular to the flux lines, and that's when most of the flux lines are being cut the quickest. And so that's when the maximum voltage will be induced. And so that's represented by the peak voltage here on this graph at 1/4 of a revolution. The conductor continues to rotate in this magnetic field, and again, this part of the conductor will eventually be at the bottom. And again, at this point, it is moving parallel to the flux lines. No voltage will be induced, and so at 1/2 of a turn, there will be no voltage induced there. And so at 1/4 of a turn, this part of the conductor connected to the red commutator was on the right brush. And so as this conductor moved down through the flux, the current was induced into the page. So the current was flowing into the page on the right through the coil and out of the page on the left. And so the current through the voltmeter is from left to right. Now at half of a revolution, that's when the brushes are at the gaps of the commutator, and as the coil continues to rotate, now the red part of the commutator is connected to the left brush. And so now this part of the coil that's on the left now, as it moves up through the flux lines, the current is going to be induced out of the page. And so the current comes out of the page, through the left brush, and from left to right through the voltmeter. That left to right direction of the electrons is the same whether the red commutator was on the right brush or the left. And that's the purpose of the commutator. It keeps the direction of electrons flowing in the same direction through the circuit, always through the voltmeter from left to right. And so the voltage induced across the voltmeter always has the same polarity, a positive polarity. And so we see what looks like a sine wave on this graph, where the negative part of the sine wave has been flipped back up into the positive. And so that flipping of that second half of this alternation is representative of the commutator switching from one brush to the other. And so the current will always flow in the same direction here. This, on the other hand, is an example of an AC generator. And so here we still have a coil. It's in a permanent magnetic field. This time, though, the ends of the coil are connected to slip rings. And so these slip rings, again, these will rotate with the coil. And the top part of the coil here is connected to this closer slip ring to the coil. And it is always connected to the right side, or toward the page side of this resistor. And the bottom part of this coil is connected to the farther slip ring, and that is always connected to the farther part of the resistor. And so here, when this coil rotates, this top part of the conductor sometimes passes down through the magnetic field and sometimes passes up through the magnetic field. And so down versus up is going to correspond to either the electrons are flowing in through that part of the conductor or out of the page through that part of the conductor. And what that results in is an alternating current. So when this part of the conductor is passing down through the magnetic field, we get a positive voltage induced, and so the current flows in one direction through the resistor. But as this coil continues to rotate and this part of the coil eventually moves up through the magnetic field, the direction of the electrons flowing in the circuit are going to be in the opposite direction. And so this is how we generate an AC current using a permanent magnetic field and a coil and slip rings. This is a bit of a review of some trigonometry ideas. So this circle has a particular radius, and this radius represents the maximum voltage that can be induced in an AC generator. And so notice that through the first 30 degrees of rotation, if the radius started out here at 0 and it rotated up to 30 degrees, the change in the y value is relatively large, but the change in the x value is relatively small. That's opposed to, say, rotating from 60 to 90 degrees, where from 60 to 90 degrees the change in the y value is relatively small, but the change in the x value is relatively large. And so if you could imagine flux lines from a permanent magnet where the north pole was at the top at the positive y and the south pole was at the bottom at the negative y, and if this arrow represented the position of the conductor, when the conductor is at 0 degrees and moving up, it's moving parallel to those flux lines, and no voltage is induced. And so that's what we see here in this graph at 0 degrees. Here at 0 degrees, there's no voltage being induced. But up here at 90 degrees, as the conductor is rotating counterclockwise, and the flux lines are directed down, that's when the conductor is moving parallel to the flux lines, and that's when the maximum voltage is going to be induced. So we started off at no volts at 0 degrees. The voltage was increasing up to a maximum value, which occurred at 90 degrees. And then as the conductor continues to turn, the conductor is still moving from right to left through the flux field. So the current is still in the same direction, but as the conductor rotates and it's moving closer and closer to being parallel to those flux lines, the voltage induced is reducing back down towards 0. And if this conductor continued to rotate, it would eventually be moving left to right through the flux field, and therefore the direction of current flow will have reversed, and that will be the negative alternation of that sine wave. We should also remind ourselves of what a radian is. A radian is defined as an angle that is swept out by a radius that is rotating in a circle, and when the arc length swept out, which is out here on the circumference, when this arc length is equal in length to the radius, the angle that forms that arc length is defined as 1 radian. And so you should remember that the circumference of a circle is equal to the diameter times pi. And since the diameter is 2 times the radius, a complete rotation is 2 pi, meaning that the circumference of the circle is equal to 2 pi times the radius. And so a complete rotation around the circle is equal to 2 pi radians. That's how many radiuses we would have to lay out on the circumference to make one complete rotation, 2 pi total. And so a complete rotation around a circle is 2 pi radians. That corresponds to 360 degrees. Half of a rotation would only be pi radians, which corresponds to 180 degrees. Pi over 2 radians would be 90 degrees, and 3 pi over 2 radians would correspond to 270 degrees. And so here on the sine wave, we can see that if a conductor was rotating in a magnetic field, that at 90 degrees, that is when the induced voltage will be maximum. This is going to be the same thing as pi over 2 radians. At 180 degrees, or pi radians, again, the voltage will be a minimum, 0 essentially, because the conductor is moving parallel to those flux lines. This is also a good time to review some trigonometry. For a right triangle, we have 3 angles. We call them A, B, and C. C is always going to be the 90-degree angle in the right triangle. And we also have 3 sides that make up the triangle, and we'll label them A, B, and C, where side A is opposite angle A, and side B is opposite of angle B. And the side C will always be the hypotenuse, that is the side opposite of the 90-degree angle. And so we define these trig functions as the ratio of the lengths of the sides. And so if we look at angle A, and we'll call here angle A has also been labeled as theta. If we look at angle A, side A is opposite of angle A, side B is adjacent to angle A, and the hypotenuse is always the hypotenuse. The sine is defined as the ratio of the opposite side of the angle divided by the hypotenuse. So for angle A, the opposite side again will be A, the hypotenuse will be C. If we divide the length of side A by the length of the hypotenuse, that will be equal to the sine of the angle A. The cosine is defined as the adjacent over the hypotenuse, so that would be B over A, and the tangent is defined as the opposite over the adjacent, so that will be side A divided by side B. There is an identity also being pointed out here that the tangent will be equal to sine divided by cosine. And so if you took A over C and you divided by B over C, the C's would cancel and you would get A over B, which is equal to the tangent. And so here again we are looking at a type of an AC generator where we have a coil that is rotating in a magnetic field, and here we're starting off, we'll call this 0 degrees, and at 0 degrees no voltage is being induced. As we start to rotate, the voltage induced starts to increase, and as the conductor reaches 90 degrees and the conductor is moving down perpendicular through the flux field, that is when the voltage will be maximum. This is section 3, it's called rate of change. So if we look at a sine wave, by rate of change we mean how rapidly is the graph changing in the y direction. And so if you look at the first 45 degrees of a rotation, the change in the y direction is relatively large. If you counted these squares, maybe 1, 2, 3, 4, 5 squares roughly are being passed through by the graph in the first 45 degrees of rotation. But if you look at the next 45 degrees, from 45 to 90, it's fewer, only maybe 1, 2, and about a half. So only about 2.5 squares are being passed through by the graph. And basically by rate of change, what we're talking about is how steep is the graph itself. So here at the peak, it's not steep at all, right? It's almost flat up here. But right here at the zeros, that is where the graph is the steepest. And so here the sine wave is changing most rapidly. Where it crosses the x-axis, that is where the most rapid rate of change is occurring. And at the peaks, whether it's a positive or a negative peak, that is where the rate of change is the least rapid. This is section 4. It's called Introductory Information, Summary Regarding AC Sine Wave Signals. And so these are some of the things that we've learned so far, and we'll summarize them here. AC signals correspond to sine waves. As a conductor rotates in a magnetic field, the voltage induced in that circuit is going to be a sine wave. And so AC signals, they're continuously changing in amplitude, and they periodically change in direction, so the value is never really constant, it's always changing. And the direction of the current flow through the circuit is periodically changing, sometimes clockwise, sometimes counterclockwise. A complete cycle is going to be equal to 360 degrees. The complete rotation of the coil in the magnetic field gives us one complete sine wave on the graph. That'll be 360 degrees of rotation, or 2 pi radians. We will consider 0 degrees as the starting point of the signal. The maximum amplitude occurs at 90 degrees. The minimum amplitude occurs at 270 degrees. And so by minimum amplitude, we mean the most negative. And so the max and the min have the same absolute value, though the maximum is positive and the minimum is negative. One cycle is measured from any point to the next point, next identical point on the wave. And so sine waves repeat themselves forever. And so if you look at a sine wave that is repeating itself, the one complete cycle is any point on the sine wave to the next identical point on that same sine wave. And so be careful, identical points have the same value in the y direction, but they also have to have the same polarity, meaning the sine wave is either increasing or decreasing at that point. And so there are points on the sine wave that have the same value, but at one point on the sine wave is decreasing, and on the other it's increasing. But that will not be one complete cycle. We have to make sure that we have the same value and the same direction. Also, the rate of change varies over the wave, and so the rate of the change of the sine wave is maximum at the 0 points where it's crossing the x-axis, and the rate of change is a minimum at the peaks, the minimum and the maximum peak. The rate of change there is essentially 0. This is section 5. It's called Some Basic Sine Wave Form Description, and that should say form, wave form, not wave from. And so this is a sine wave, and these are some of the important characteristics of sine waves that we want to make sure that we remember, and this is how we label them. Sine waves have two alternations. One is called the positive alternation, shown here in a sort of a pinkish color, and the negative alternation here shown in this blue color. And so the positive alternation represents the time at which the current is flowing in one direction through the circuit, and the negative alternation represents the time in which the current is flowing the opposite direction in the circuit. And so the maximum value of either alternation off of the x-axis, we call that the peak value. And so if this sine wave is representing voltage, this voltage will have a peak voltage value. And we also have a similar peak value for the negative alternation. They have the same absolute value, but for the positive alternation, the peak is a positive value. For the negative alternation, the peak is a negative value. We also have what we call the peak-to-peak, and that is the difference in the positive peak minus the negative peak. And so let's say that this sine wave represents voltage, where the peak value is positive 10 volts, and the peak value on the negative alternation is negative 10 volts. Then the peak-to-peak value will be the positive 10 volts minus this negative 10 volts. And positive 10 minus negative 10 is 20. And so the peak-to-peak tells us the range of voltage from one peak to the other. And so again, if each peak was 10 volts, the peak-to-peak would be 20 volts. The positive and negative alternations, we can also call those positive and negative half cycles. And so each half cycle, when put together, is equal to one whole full cycle. This is section 6, period and frequency. Periodic waves, which are sine waves, sine waves are periodic waves. They repeat themselves in time and form. And so a sine wave is a periodic wave because it runs on forever. It repeats itself. Every time it repeats itself, it's exactly the same, and it takes the same amount of time for it to repeat itself each time that it does. And so periodic waves have what we call the period. That is the time it takes to complete one complete revolution. So for example, household AC has a period of 1/60th of a second, meaning that every 60th of a second, the voltage coming out of your outlet makes one complete alternation, right? Each 1/60th of a second we get one complete alternation. The frequency, that is the number of cycles occurring in 1 second. And so for example, your household AC, if the period is 1/60th of a second, that means that we're getting 60 periods or 60 oscillations or 60 repetitions every second. And so every second we get 60 individual little sine waves that form this full sine wave. And so period and frequency are inverse of one another. One is the reciprocal of the other. And they vary indirectly. That means that when one gets larger, the other gets smaller. If the time it takes a sine wave to complete one full period is increased, we can fit fewer of those sine waves in 1 second. And so if the period gets larger, the frequency will get smaller. And so it follows a relatively simple formula. The period, which is t, is going to be equal 1 divided by the frequency, which is f. The period is measured in seconds, that's a unit of time, and the frequency is measured in hertz. That is a unit of counting how many things happen in a given unit of time. And so hertz means how many times does something repeat itself each second. And so in these examples, what is the period of a sine wave that has 100 hertz as its frequency? And so to find the period, we take 1 divided by the frequency. 1 divided by 100 would be 0.01. Or 10 milli, and so the period will be 10 milliseconds. What is the period of a 1000 hertz sine wave? And so again, 1 divided by the frequency, 1 divided by 1000 hertz is going to be 0.001 seconds, or 1 millisecond. And likewise, the frequency is going to be 1 divided by the period. And so what is the frequency of a signal with a period of 0.0001? And so I'm going to use my calculator here. 1 divided by 0.0001 is equal to 10,000, or 10 kilo. And so the frequency will be 10 kilohertz. And the second one here, what is the frequency of a signal with a period of 0.005? So again, I'll use my calculator. 1 divided by 0.005 is 200. And so the frequency will be 200 hertz if the period is 0.005 seconds. This is section 7, phase relationships. And so we are talking about sine waves, and they have period and frequency. And when we have two different sine waves, they can be said to be in phase or out of phase. And so the difference in angle between two waves with the same frequency is called the phase angle. And so we may have two conductors that are bent into coils, and they're rotating in a magnetic field, but when one is at 0 degrees, the other may be at 45 degrees or at 90 degrees. And so the voltage induced in those two conductors will not be in phase with one another. One of the conductors will be moving parallel to the flux lines when the other one is perpendicular. And so one will have an induced voltage while the other one does not. So waves of the same frequency that cross the 0 voltage point at the same time and are going in the same direction, either increasing or decreasing, those are said to be in phase. And so if you look at this figure here, we have three different sine waves, A, B, and C, and they all have the same period. The time it takes to complete one oscillation of any one of these three sine waves is the same. Okay, the time that it takes is equal, so they have the same period. And A and B are in phase because they are both at 0 at the same time. They both rise to their maximum value at the same time. They drop back down to 0 at the same time. They drop back down to their minimum value at the same time, and they rise back to 0 at the same time. So A and B are two sine waves that we say are in phase. Now if you look at A versus C, when A is at 0, C is at a minimum. When A rises to its maximum, C is at 0. When A falls back to 0, C is rising to its maximum. When A is falling down to the minimum, that's when C is falling back to 0. And when A rises back up to 0, that is when C is falling down to its minimum. And so A and C are not in phase. They do not have the same values at the same point in time. And they are out of phase by a certain angle, or the phase angle. And so you can see that the peak value of A and the peak value of C are out of phase by 90 degrees. So A is at a maximum at 90 degrees, and C is at a maximum at 180 degrees. The phase angle between the two will be 90 degrees, right? 180 minus 90 is 90. And so we can represent these sine waves as vectors that are rotating. And so again, you can think of this as a coil where we have a flux field, maybe directed downward. And so when these are A and B, these are our vectors that are rotating in the flux field. When A is moving straight up and getting ready to go back to the left, B is moving slightly to the right and also upward. And so they're not in phase with each other. In fact, they're out of phase by 45 degrees. And so A has 0 voltage induced when B has not a maximum value, but not a 0 either. And eventually, if these continue to rotate, B will be passing up where A was before, but A will be 45 degrees ahead. And so we see that A will reach its maximum value first. And so A will be at its maximum value when it's moving straight from the right to the left at the maximum value up here as it continues to rotate. At that time, B will be behind. It will come up to its maximum point sometime later. And so we see that in the graph. A rises to its maximum value first. B is rising to its maximum value sometime later. And so the phase angle between the two is 45 degrees. And so if A is 360 degrees to complete a full revolution, and so is B, by proportion we would see that from peak of A to peak of B would be equal to 45 degrees. Example B here shows two phasors. A phasor is another word for a vector that rotates. Two phasors are shown here in example B that are 180 degrees out of phase. And so we see what their sine waves would look like here. When A is passing from right to left through the magnetic field, B would be passing from left to right, and therefore A would be having a maximum voltage induced in it at that time when B has a minimum voltage induced in it. And so this is what we see when we have two phasors that are 180 degrees out of phase. And figure C shows two phasors that are 90 degrees out of phase. So again, if the flux field was directed from top to bottom, and A was moving from right to left, cutting the flux lines perpendicular, that's when A would have its maximum voltage being induced in it. And at that same time, B is moving up through the field, and therefore it's moving parallel to the flux lines, and it will have a 0 voltage induced in it. And when B makes its way to the peak, that is when A will be over here at 180 degrees. A will be moving parallel to the flux lines when B is moving perpendicular, and so B will be at a maximum when A is at 0. And so this is what two phasors look like when they are 90 degrees out of phase. This is section 8. It's called Important AC Sine Wave Current and Voltage Values. And so we've been looking at these sine waves, and so a sine wave is a periodic waveform that is always changing in value, right? The Y value is always changing, and it's periodically changing in polarity. Sometimes it's positive and sometimes it's negative. And so we've talked about some of this already. The peak value is defined as the value from the x-axis to either the maximum or from the x-axis down to the minimum, and so we'll have a positive peak or a negative peak. Again, they have the same absolute value, but they have different sign. And the peak to peak will be equal to the positive peak minus the negative peak. So in my example before, if this represented a 10 volts peak, this would be negative 10 volts peak, and the peak to peak will be 10 minus negative 10, which is 20, and so the peak to peak value here would be 20 volts. We also have two other values that we're looking at here. One of them, first of all, is the average value. And so if we could cut up this pink section of the sine wave into a very large number of very small squares, right? We cut this up into a lot of very small squares, and we were to, we were to restack those squares so that the waveform was level, no longer a sine wave, but rather more like a rectangle. Well, if we moved all of these squares down to fill these gaps, the value of the rectangular wave would be the average here. And this value of 0.637, we can prove that using calculus, so we won't do that here. But you want to keep this in mind. This average value is a value that we'll use a lot more in analog circuits. For AC circuits, we're really interested in what we call the RMS value. This is called the RMS stands for the root mean square. And so what that means is if we could take points along the sine wave and we could find their Y values for a whole bunch of points along the sine wave here, We took all of those values and we squared them all. We added all of those squares together and averaged them, divided by how many there were, and then whatever that average was, we took the square root. That would give us the root mean square. And so again, that means that we're squaring all of the values, and then we're averaging them, and then we're taking the square root, the root of the average of the square, or the root mean square. Mean is another word for average. And so if we were to do that, the value that we get is going to be equal to 0.707 times the peak value. And again, we can prove that with calculus. We won't bother doing that. We just want to make sure that we remember this formula. The peak value, if we multiply it by 0.707, we get is what is called the RMS value. Now the RMS value is important because it is the equivalent AC voltage to a DC voltage that has the same power dissipation value. And so an AC sine wave of a particular peak, that peak value is not really of a very high importance to us. The value of the voltage is not always at that peak value. Rather, the root mean square of the voltage over time is going to be about 0.707 times the peak. And so, for example, let's say that the peak value here was 10 volts. The RMS value would be 7.07 volts. This AC sine wave would be dissipating the same amount of power as a DC circuit that was at 7.07 volts. And so that's really important to us. We want to make the connection between AC and DC with the respective power quantities. Two circuits that have equivalent power dissipations are essentially going to be equivalent. And so these are some of the notations that we use. The peak value of a sine wave we abbreviate as VP. It could be abbreviated as VM, where M would stand for maximum. P stands for peak. I will use VP in this course, not VM. We can do the same thing with current. When the voltage is changing as a sine wave, the current will also be changing as a sine wave, and so the current will have a peak value just like the voltage does. VP-P stands for VP, the voltage peak to peak, which is again the maximum peak minus the minimum peak. And the peak value of the voltage is always going to be 1/2 of the peak to peak, for a sine wave at least, right? Always for a sine wave, the peak value is going to be 1/2 of the peak to peak voltage, or the peak to peak will be 2 times the peak voltage. So these last two formulae here, you want to make sure that you remember these. If you know peak to peak, you can take half of that to get the peak, and if you know peak, you can multiply by 2 to get the peak to peak. We also want to remember these two formulas for the RMS value, which is the effective value, which is a very important value in this class. You really want to make sure that you remember this one. 0.707 times the peak value gives you the RMS value, and the average value, which we will use in the next course, will be 0.637 times the peak value. So you want to make sure that you remember these formulas. This is section 9. It's called the purely resistive AC circuit. And so by purely resistive, we mean a circuit, an AC circuit that only has a resistor in it, no inductors and no capacitors. As long as the circuit is purely resistive, the voltage and the current will be in phase. And we'll see later that if we start to add inductors and capacitors to the circuit, the voltage and the current start to become out of phase. The voltage will peak at a different time than the current does. And so as long as the circuit is purely resistive, though, they will peak at the same time, they will cross the zeros at the same time, and they will have a minimum peak at the same time, and they will cross at the 0 point again. And so this is fairly intuitive. This says that if the voltage is at a maximum value in the circuit, well, then the current must also be at a maximum value. That's Ohm's law. If the voltage goes up, the current should go up as well. If the voltage was 0, the current should be 0. And again, we'll see later that if we add inductors and capacitors to these circuits, that's not going to be the case anymore. And so we'll explore that in more detail in later sections. This formula says that the instantaneous voltage, which is denoted with a lowercase, sort of a cursive type V, the instantaneous voltage is equal to the peak voltage times the sine of the angle. And so in a sine wave, it has an infinite number of values. And let me go back up here. I'll find a sine wave to look at. There's an infinite number of values along this sine wave, right? Between the peak to 0 can be divided up into an infinite number. And actually, let me go back even farther, and I will find a better picture here that I want to look at. This one. So this radius started off at 0 degrees and it rotated up to 30. And so the instantaneous voltage in the circuit would be equivalent to the length of this side opposite of this angle. And so for this angle, which is 30 degrees, if we knew the hypotenuse, which is going to be the peak voltage, because when this vector is all the way up, that is the maximum value that the sine wave can achieve. If we know the value of the hypotenuse, which is the peak voltage, and we know the angle at which we are in the rotation, if we multiply the hypotenuse by the sine of the angle, we get the opposite side. So the sine is defined as the opposite over the hypotenuse. So if we know the hypotenuse and we multiply by the sine of the angle, we get the instantaneous voltage at this point in time. And so that is what this formula is telling us, that the instantaneous voltage will be equal to the peak voltage, which again is the value of the vector, the magnitude of the vector. The peak voltage times the sine of the angle gives us the instantaneous voltage at that point in time. And so here we see a simple circuit. Anytime we do calculations in simple circuits, let's take a look at a simple AC circuit. Here we have a circuit with 100 volts RMS source and two 10 kilo ohm resistors in series. Now the voltage was already given to us in RMS. We are almost always wanting the RMS value when we're looking at AC circuits, because the RMS value tells us the value of the voltage of an equivalent DC circuit that has the same power dissipation effects in the circuit. And so the peak voltage of 100 volts RMS would be 141.4 volts. We're almost never interested in the peak voltage, almost always in the RMS voltage. And so as long as we use the RMS value for voltage and current, we can solve these purely resistive circuits much the same way we would a DC circuit. Ohm's law still holds true, and Kirchhoff's voltage and current laws still hold true as well. And so we already have the RMS voltage. We're going to go through the same procedure we would for a simple DC circuit. And so first thing we'll do is find the total resistance, which of course is R1 plus R2, which would be 10 kilo ohms plus 10 kilo ohms. The total resistance is 20 kilo ohms. Okay, and so total resistance is 20 kilo ohms. Next step is to find total current. Total current will be the source voltage divided by the resistance. And again, when we do our calculations, we're always going to use the RMS value for voltage, and we're always going to be finding or using the RMS values for currents. And so the source voltage is 100 volts RMS. The resistance value is 20 kilo ohms. And so the total current will be 100 volts divided by 20 kilo ohms, which is going to be 5 milliamps. Okay, so the total current in the circuit is 5 milliamps. And since this is a series circuit, the current in each of the resistors will be equal to the total current. So this will be 5 milliamps here and 5 milliamps here. And so it doesn't matter which direction the current is going in, the RMS value of the current will be 5 milliamps. Okay, so just like we saw in the sine waves in previous examples, the RMS value is the effective current flowing in the circuit. And so now we can find the voltage drops. Voltage drops on R1 will be R1 times the current through R1. And so VR1 will be equal to 10 kilo ohms times 5 milliamps. And so I'll just type it in so you can see. 10 kilo ohms times 5 milliamps is going to be 50. VR1 will be 50 volts. VR1 is 50 volts. And so VR2 is also going to be 50 volts because I still have 10 kilo ohms, 5 milliamps. We will have 50 volts here. And we can see that Kirchhoff's voltage law here is holding true, which says that the sum of the voltage drops in the circuit has to equal to the total voltage of the circuit. And so here 50 plus 50, of course, is 100. And so while we're on topic here, we'll also find the power in the circuit. The power in the circuit is equal to the voltage times the current. The source voltage times the total current gives us the total power. And so the source voltage is 100 volts. And again, I'm using the RMS values to find this. So So remember, the RMS value for voltage in an AC circuit tells me the equivalent DC voltage with the same power effects. So it makes sense that I'm using the RMS voltage here and the RMS current to find the true power, or the total power of the circuit. Right, so these are the values of the equivalent DC circuit that give me the same power used in this circuit. And so 100 volts times 5 milliamps is going to be 500. The total power will be 500 milliwatts. Total power of the circuit is 500 milliwatts. Now we could find the power dissipated by R1 and the power dissipated by R2. The power used by R1 will be the voltage drop on R1 times the current through R1, and so power in R1 will be equal to 50 volts times 5 milliamps, and so the power in R1 will be equal to 250 milliwatts, and so I'll type that in for you. 50 volts times 5 milliamps is going to be 250 milliwatts. I could put my calculator in engineering mode for you, and so 0.25 is 250 milli, and so we have 250 milliwatts for R1. We're going to have the exact same value here for R2 because we have the same voltage and the same current, and the power dissipated by each resistor adds up to be the power, the total power dissipated by the circuit. In this example, we will look at a simple AC circuit that has two resistors in parallel, and again we will solve this the exact same way that we would solve a DC circuit, and again we can only do that because this is a purely resistive circuit. There are no inductors or capacitors, which we'll take a much closer look at as the course progresses. And so again we have 100 volts RMS, and we have R1 and R2, and they're both 10 kilo ohms. And so again the RMS value is the effective voltage, that is the equivalent voltage of a DC circuit that produces the same power dissipation properties. And so we're going to do the same thing we would do for any circuit. We'll start by finding the total resistance. And so the total resistance in a parallel circuit will be the product divided by the sum. So the total resistance will be R1 times R2 divided by R1 plus R2. So the total resistance will be 10 kilo ohms times 10 kilo ohms divided by 10 kilo ohms plus 10 kilo ohms. And so the total resistance was, I'll type it in so we can see, 10 kilo times 10 kilo, which is going to be 100 mega ohms squared. 100 mega ohms squared. 10 kilo plus 10 kilo is 20 kilo. Spare you the calculator on that one. The total resistance then will be this 100 mega ohms squared divided by 20 kilo ohms. Total resistance is 5 kilo ohms. Okay. And so that doesn't matter if the circuit is AC or DC, right? The total resistance is calculated exactly the same way. It doesn't matter if it's AC or DC. And when we have two resistors in parallel and they have the same value, we expect their total resistance to be half. And that's exactly what we get here. And so now the next step is to find the total current, which will be the source voltage divided by the total resistance, source voltage in RMS value. So this will be 100 volts divided by 5 kilo ohms. And so the total current of the circuit will be 100 volts divided by 5 kilo ohms, which is going to be 20 milliamps. The total current in this circuit is 20 milliamps. And so the total resistance was 5 kilo ohms. Total current is 20 milliamps. And so that total current sometimes leaves this terminal of the circuit and flows this way. This is the total current in the circuit. When it reaches this node, some of the current flows this way, call that I1, and some of the current flows this way, we'll call that I2. Right, so when the total current reaches this node, it splits. I1 flows this way, and I2 flows this way. Now sometimes the total current leaves this terminal, reaches this node, and splits, and flows down through R1 and R2 as opposed to up. Well, it doesn't matter. The RMS value being the equivalent DC voltage, accounts for that for us. And we only need to analyze the circuit when the current flows in one direction or the other. We don't need to do both. Okay, the RMS voltage already takes care of all of that for us. It's given us the effective values of the circuit. And so to finish solving the circuit, the thing that we know is that because R1 and R2 are in parallel, and they're also in parallel with the source, is that they have the same voltage across them, right? They all have 100 volts across them. And so the voltage for R1 is 100 volts, and the voltage for R2 is also 100 volts. And so we can find the currents in R1 and R2 by taking the voltage divided by the resistance. And so the current for, let's say, R1 will be the voltage on R1 divided by R1. And so the current through R1 will be equal to 100 volts divided by 10 kilo ohms. And so I'll go ahead and type this in for you. 100 volts divided by 10 kilo ohms is going to be 10 milliamps. 10 milliamps. And so the current here is 10 milliamps. We're going to get the exact same current for R2 because we still have 100 volts and we still have 10 kilo ohms, and when we divide we will get 10 milliamps. And so now we can find the power in R1 and R2, and we'll also find the total power. Oh, before I do, I should point out that the current in R1 and the current in R2 still adds up to be equal to the total current. That's Kirchhoff's current law, right? And so the total power will be the source voltage times the total current. And so the total power in the circuit will be 100 volts times 20 milliamps. And so 100 volts times 20 milliamps is going to be 2 watts. The total power of the circuit is 2 watts. And so let's find the power in R1, which would be the voltage in R1 times the current through R1. And so the power for R1 will be equal to 100 volts times the current through R1, which is 10 milliamps. And the power in R1 will be 100 volts times 10 milliamps, which is going to be 1 watt. 1 watt. And so the power in R1 is 1 watt. Power in R2 will also be 1 watt because we have the same voltage and the same current that we did before. And the total power of the circuit, I didn't write it, 2 watts. The total power of the circuit, 2 watts, is equal to the sum of all of the power drops in the circuit. And so now we've solved the circuit. Okay, one last example here for simple AC circuits. This time we have a series parallel combination. We have R1, R2, and R3. R2 and R3 are in parallel. That's all in series with R1. And all three resistance values are 10 kilo ohms. The source value of the voltage is 100 volts. And so again, we're going to start by finding the total resistance. And so we need to combine R2 and R3 first. They're farthest from the source. They're in parallel. We will combine those first. And so R2 in parallel with 3 will be R2 times R3 divided by R2 plus R3, product over sum. And so R2 in parallel with 3 will be 10 kilo ohms times 10 kilo ohms divided by 10 kilo ohms plus 10 kilo ohms. And this is the exact same problem that we had in the previous example. R2 in parallel with R3 will be equal to 5 kilo ohms. And again, when two resistors are in parallel and they have the same value, we expect their combined resistance to be half of their individual resistances. And so now we have R2 and R3 as one resistor, and that is all in series with R1. And so the total resistance will be equal to R1 plus the combination of 2 in parallel with 3. And so the total resistance of the circuit will be 10 kilo ohms plus 5 kilo ohms, which is the combination of 2 and 3. And so the total resistance will be 15 kilo ohms. 15 kilo ohms. So total resistance is 15 kilo ohms. And we will continue on like normal. Next step is to find the total current, which will be the source voltage divided by the total resistance, which will be 100 volts. Again, always in the RMS value. 100 volts is already in an RMS value for us, divided by 15 kilo ohms. And so the total current will be 100 volts divided by 15 kilo ohms. and we get 6.67 milliamps. So the total current in this circuit will be 6.67 milliamps. That's the total current in the circuit. And so that total current is an RMS value. That entire current flows through R1, right? And again, it doesn't matter which direction it's flowing. Either direction it flows, 6.67 is the RMS value. And so the total current here is 6.67 milliamps. And so now that I know the resistance and the current in R1, I can find the voltage drop. So I'll start up here. The voltage drop in R1 will be equal to R1 times the current through R1. And so the voltage drop in R1 will be 10 kiloohms times 6.67 milliamps. And so VR1 will be 10 kiloohms times 6.67 milliamps. And so the voltage drop is 66.7 volts. 66.7 volts. Okay, and so voltage drop here is 66.7 volts. And so now the next step is, because R1 and R2 are in a loop with the source voltage, their voltage drops must sum up to the source voltage. And so R2 will be equal to the source voltage minus the voltage drop on R1. Right, so R1 plus R2 has to equal the source voltage. R2 will be equal to 100 volts minus 66.7 volts. And I'm sorry, this should say VR2. Okay, so the voltage drop on R2 will be equal to 100 minus 66.7, which is going to be 33.3 volts. 33.3 volts. And R2 and R3 are in parallel. They have the same voltage drop. And so 33.3 plus 66.7 equals 100, or 33.3 over here plus 66.7 also equals 100. They have the same voltage drop on them, 33.3 volts. And so now we can find the currents in R2 and R3. And so the current in R2 will be equal to the voltage drop across R2 divided by the resistance value of R2. And so the voltage drop is 33.3 volts. The resistance value is 10 kiloohms. And so the current through R2 will be 33.3 volts divided by 10 kiloohms, which is 3.33 milliamps. 3.33 milliamps. And so the current here is 3.33 milliamps. Now I'm going to get the same answer for R3 because they have the same resistance and the same voltage, and so R3 will have the same current as well. The current here is also 3.33 milliamps. And Kirchhoff's current law says that as the current flows through R1, this is the total current, when it reaches this node, it splits, and some of that current flows through R2, and some of it flows through R3. And so this will be I2, this will be I3. And so I2 and I3 should sum up to give us the current through R1. And so 3.33 plus 3.33 is 6.66, and so minus a little bit of rounding error, that is in fact the case. And so the last step maybe would be to look at some of the powers. The total power in the circuit will be voltage times current. So to save space, I'm just going to write 100 volts times 6.67 milliamps. And so 100 volts times 6.67 milliamps. Oops, I'm sorry. How about 0.00667 for milliamps is going to be 667 milliwatts. The total power of the circuit is 667 milliwatts. Okay, so that's the total power, 667 milliwatts. And we want to find the power in each of the three resistors. So the power of resistor 1 will be 66.7 volts times 6.67 milliamps. So So 66.7 volts times 6.67 milliamps is going to be 440, let's say 445 milliwatts. The power in R2 will be the voltage, which is 33.3 volts, times the current, which is 3.33 milliamps. And so we have 33.3 volts times 3.33 milliamps, and we're going to get 111 milliwatts. Well, the power in R3 is going to be the same as R2 because they have the same voltage and the same current, and so it'll also be 111 milliwatts. And so let me write these up here. We have 445 milliwatts for R1, and we have 111 milliwatts for R2 and R3. And so this is a good reminder for us that the sum of all of the powers in the circuit, regardless of whether the components are in series or parallel, should add up to the total power of the circuit. And you can see that 445 plus 111 plus 111 is in fact 667. And so this is a good way for us to check our answers. And so the circuit is solved. This is section 10. It's called Other Periodic Waveforms. And so we've been looking at sine waves specifically. Most of our AC signals are going to be in the form of sine waves, but it's possible that they're in other forms. We can have square waves, and so in a square wave, the positive alternation is equal in duration to the negative alternation, so they're symmetrical. But the rectangular wave is a wave in which the time that the signal is high and the time that the signal is low are not necessarily equal, whereas in a square wave they were equal. So that will be the rectangular wave. We can also have sawtooth waves where the value of the voltage rises linearly and then also decreases linearly, and the time that it takes for the signal to rise and the time that it takes for the signal to fall do not necessarily have to be equal. And so we'll call that a sawtooth wave. And so this is just a little bit about how square waves are generated. This is based on Fourier analysis, which basically says that any type of waveform is basically the sum of sine waves. And so here you can see that we have a sine wave with a fundamental frequency here and a fundamental period. And so that's the longest period sine wave that you see here. And then we have a sine wave that is the third harmonic. And so what that means is that the period is 1/3 of that of the original wave. So the original wave had a period of this entire time, and the third harmonic's period is 3 times, right? So we get in 3 oscillations of the third harmonic to only 1 oscillation of the fundamental sine wave. And when we add the fundamental sine wave to the third harmonic, we get this waveform here in red. And so you can see that the waveform goes high, and it kind of stays high for a while. Even though it's fluctuating, it's still positive, and then as it decreases, then it kind of hangs out down here for a while, and again it's fluctuating, but it's relatively low. And so if we added the fundamental with the third harmonic and the fifth harmonic, if we added those all together, the sine wave would start to approach something that looks more and more like a square wave. And so if we added in the 7th and the 9th and the 11th and so on, we would eventually get something that looks like a very pure sine wave. So that's sort of represented here, just to give us an idea of how these square waves are generated. And so there is the sawtooth wave that we've already kind of talked about. There's also the triangular wave, which is just symmetrical. And so the triangular wave has the same amount of time for rising as it does for falling, and it's symmetrical, right? So it takes the same amount of time to rise as it does to fall. Whereas the sawtooth wave is not symmetrical. It may take longer to rise and then a short period of time to fall, or vice versa. And so the purely resistive AC circuit, important parameters for non-sinusoidal waveforms. We determine the period the same way. The period is the amount of time it takes the waveform to complete one full cycle. We can determine the peak-to-peak values in the exact same way. Whatever the maximum value is minus the minimum value tells us the peak-to-peak. but we cannot use the 0.707 times the peak value to find the RMS value. That will not work. That only works for sine waves. Does not work for any other kind of wave. So 0.707 is for sine waves only. And so when we look at rectangular waves or square waves, these are some important parameters that we need to keep in mind. The pulse width, we call the amount of time that the signal is high the pulse width, and so the pulse width is measured in seconds. How long is the signal high for? The period, of course, is the time it takes the signal to complete one full oscillation, so from the time that it rises until the time that it's getting ready to rise again, that amount of time that passes is the period. And the baseline, that is the lowest value of the waveform, and so the baseline is not always 0. It could be some other value. And so we want to be able to calculate duty cycle, and the duty cycle basically tells us what percentage of the time is the signal high. And so we calculate the duty cycle by taking the pulse width, which is the amount of time that the signal is high, right, measured in seconds, divided by the period, which is the total amount of time it takes for one complete oscillation. And so when we divide these and multiply by 100%, that tells us what percentage of time is the signal high versus 100% for the entire period. And so this will be our formula for duty cycle. Let's take a look at an example. It says if the time for one period of a repetitive pulse signal is 20 microseconds and the pulse width is 4 microseconds, then the percentage duty cycle is. And so they tell us that the period of the waveform, the total period, is 20 microseconds. That's the amount of time it takes to complete one complete oscillation of this repetitive cycle. And the pulse width is 4 microseconds. 4 microseconds. And so the formula that we have is that the percent duty cycle is equal to the pulse width divided by the period times 100%. And so we'll just plug in our numbers here. The percent duty cycle will be equal to 4 microseconds divided by 20 microseconds times 100%. And so the microseconds will cancel. One in the numerator, one in the denominator. They cancel. And so the percent duty cycle will be, it's going to be 4 divided by 20 and then times 100. And so the duty cycle is 20%. 20%. And so 4 microseconds is 20% of 20 microseconds. In other words, the signal is high 20% of the time, and then the other 80% of the time the signal is low. And so the duty cycle will be 20%. So we've seen that to find the average value of a sinusoidal waveform, we would multiply the peak value by 0.637. That's only going to work for sine waves though. If it was a square or a rectangular wave, we can still calculate the average voltage, and we will do that by using this formula, formula 11-7. This says that the average voltage is equal to the baseline value plus the quantity of the duty cycle times the peak-to-peak amplitude. And so we'll look at a couple of different waveforms here. You can see that they are rectangular waves. They have pulse widths, right? So there's a certain amount of time that the signal is high, and they also tell us the period, the entire time it takes to make a complete oscillation of that waveform. And so here the baseline is defined as the lowest value of the waveform. And so you can see that in example C here, the baseline value is 0 volts. But here in example B, the baseline value, the lowest value of the waveform, is 2 volts. Right, so this waveform never goes below 2 volts. That'll be the baseline. And here again, the baseline value is going to be 0 volts. The dotted lines that you see here, these are the solutions to the average of the average voltage. The solution here will be 0.5, solution here will be 2.5, and the solution here, I think maybe they didn't give it to us, but we will solve these. We will calculate the average voltage of these in the next video. This is example A of this set of problems. They want us to find the average voltage of this signal. And so we have a signal here that's a rectangular wave. It has a pulse width of 1 millisecond, and it has a total period of 10 milliseconds. And the signal varies between 0 volts and 5 volts. And so when they're asking us for the average voltage, what they're asking us for is if you could take this hump, right? If you could take this hump and divide it up into a bunch of little squares and spread those squares out evenly, what value would the waveform be if we smooth this out so that instead of having 5 volts for this amount of time and 0 volts for this amount of time, what value would it be if it was even the entire time? And so to think about this, what that means is we want to essentially find the area of the rectangle here, right? The area. And so the length of this rectangle is 1 millisecond, and the height of this rectangle is 5 volts. And so the width here is the pulse width, and the height here is the voltage. And so the area of this rectangle, I'll write this up here, the area of this rectangle is the pulse width times 5 volts, which happens to be the peak-to-peak voltage. That's the peak-to-peak voltage. Okay, and so that takes the area of the rectangle, and if we wanted to spread that area out evenly, we would divide by the period. We would divide by the period. And so the average voltage would be the pulse width times the peak-to-peak voltage, which is the area of the rectangle, divided by the period of the whole cycle. So that's going to average this voltage out and spread it out evenly. And so if you look at this formula that I've written here, TW over T, well, that's the duty cycle, right? The duty cycle is multiplied by 100% if we want to express it as a percentage. Without that, it'll be a decimal. And in this formula, that's actually what we want. The duty cycle here needs to be a decimal so that we can multiply by the peak to peak. And so what this says is that the average voltage is equal to TW over T, which is the duty cycle, times V peak to peak. Okay. Which is exactly what this formula says, except for plus the baseline voltage. And so if this didn't go all the way down to 0 volts, maybe it only went down to 2 volts, the peak-to-peak voltage then from 2 volts to 5 volts would only be 3, so we would use 3 volts here instead of 5, but we would add in that 2 volts as the baseline. And that's what this formula says to do. And so let's solve the problem. The average voltage for this waveform would be the baseline voltage, which in this example happens to be 0, that's the lowest voltage of the signal, plus the duty cycle, which is going to be the pulse divided by the period, so 1 divided by 10, and that's 1 milliseconds divided by 10 milliseconds. The milliseconds here is going to cancel, times the peak-to-peak voltage, which is 5 volts. Okay, and so again, I've got the baseline voltage, which was 0, plus the duty cycle, right? The duty cycle, which is the pulse width over the period, 1 over 10, times V peak to peak, which is 5. And so again, the milliseconds here will cancel, and the average voltage will be equal to 1 divided by 10, which I'll write that as a decimal, 0.1, right? 1 divided by 10 is 1/10, times 5 volts. And so the average voltage will be 0.5 volts, 1/2 of a volt. And so if we could cut this up and spread it out as evenly as we could, this area would be able to fill this area. And so the average voltage here would be 0.5 volts. Example B looks like this. We still have the same 1 millisecond for the pulse width and 10 milliseconds for the period. The difference here being that the baseline voltage this time is 2 volts. And so this square wave rises up to 7 volts and then falls down to 2 and never falls all the way down to 0. So it varies between 2 and 7 volts, and it will repeat itself over here as time goes on. And so we'll use this formula. The average voltage will be equal to the baseline voltage, which in this case is 2. That is the lowest voltage of the signal. So that'll be 2 volts, plus the duty cycle, which the duty cycle is the pulse width, which is 1 millisecond, divided by the period, which is 10 milliseconds. This will be the decimal version of the duty cycle, right, not the percentage, so I left off the multiply by 100% part, times the peak-to-peak voltage. And so the peak-to-peak voltage of the signal, peak-to-peak voltage is always the maximum voltage minus the minimum voltage. And so max is 7, minimum is 2, 7 minus 2 is 5. And so that means that this signal varies by 5 volts, right? From 2 to 7 is 5 volts. And so the peak-to-peak voltage here is 5 volts. And so the average voltage will be 2 volts plus 0.1. The milliseconds cancels, times 5 volts. And so the average voltage will be 2 volts plus 0.5 volts. And that's a V. So the average voltage will be 2 volts plus 0.5, which is 2.5 volts. And so again, if we could cut this rectangle up into little pieces and flatten it out so that it was as even as it could be, this value would be 2.5 volts, and that is the average value of this signal. One last example here. This time we have a rectangular wave with a pulse width of 2 milliseconds, a period of 30 milliseconds, a voltage that varies from 0 volts up to 6 volts. And so this time the baseline will be 0 volts. And so the average voltage will be the baseline value, which is 0 volts, plus the duty cycle, which is going to be pulse width divided by period, so 2 milliseconds divided by 30 milliseconds, times the peak-to-peak voltage. And so the peak-to-peak voltage here is 6 volts, right? 6 minus 0 is 6, so 6 volts. And so the average voltage will be 0 plus, I don't need that part, right? It's 0. Here the milliseconds will cancel, and so 2 divided by 30 is going to be, I want to write this out as a decimal rather than engineering notation. It's 0.0667 volts plus 6 volts. Oh, I'm sorry, not plus, times. And so the average voltage will be 0.0667 times 6. And so the average voltage is 400 millivolts. Okay. And so the period here is so long that if we were to divide this up and spread it out evenly, that it would be spread very thin, a little less than half of a volt. And so here the average voltage is going to be 400 millivolts.